Everyone, Mr. Fig back again. This week we're going to look at the behavior of lenses. We'll use refraction to explain the properties of lenses and develop our ray model just like we did with spherical mirrors. I'm holding a lens right now. Here's a rather large glass lens taken from a projection system. And we're going to use what we understand of Snell's law and refraction to explain how a lens, a piece of glass like this, can be used to create images. And for example, this lens can be used as a magnifier, as you can see if I hold it in front of my eyes. There you go, right? And you can see it will magnify the image of my eye. So let's take a look at the behavior of lenses. All right, first, we need to understand that the words convex and concave describe the shape of a mirror, or in this case, the shape of a lens. A convex lens is generally a lens that is thicker in the middle. This is an example of a convex lens. To be more precise, a plano convex lens. Flat plano, flat on one side, bulging on the other side. All three of these examples in the picture here show lenses that are thicker in the middle and would act as a convex lens. A convex lens will take parallel rays and cause them to converge to the focal point. So a convex lens takes rays parallel to the principal axis, that is the center line of the lens. Rays that are parallel to that center line will bend inwards towards the principal axis and converge. Well, a concave lens, when we think of a concave lens, we typically think of the hourglass shape, which is the profile of a concave lens. But any lens that's thinner in the middle will act as a concave lens. A concave lens will take rays parallel to the principal axis and spread them out, causing the rays to diverge. So any ray that's parallel to the principal axis, that is again the center line of the lens, when it strikes the lens, will bend outwards. So I'd like to take some time to use refraction, what we understand of refraction, to see why light rays behave this way. So here is the cross-section profile of a convex lens, what we typically in a first-year physics class refer to as a convex lens. To be more precise, this is a spherical convex lens. One is based on the symmetry of a sphere. It is symmetric. That means it's the same on both sides of the lens. You can make a lens that has a different curvature on one side. We're not going to consider those types of lenses. And they're thin, so I don't have to worry too much about dispersion. Much thinner than what this diagram shows. All right, so to understand how similar lenses are to mirrors, let's take a look at this geometry a little bit more. So here I have the cross-section of a piece of glass, thicker in the middle. Well, the curvature of that glass is described as by a sphere, or in this case, a projection of a sphere, a circle. And that circle will have a center. Now, just like with a spherical mirror, we can define the focal point to be the midway point between the middle of the lens and the center. Now, here I've marked the focal point, and I replace the center of curvature with twice the focal point. If you remember, the focal point was half the radius of the sphere, so the center is actually from the edge of the lens, the center will be twice the focal length. But because we're dealing with a symmetric piece of glass, I'm going to have the same focal point on the other side of the lens. So unlike a mirror where I was concerned with a focal point on only one side because light could not penetrate through a mirror, for a lens, we have focal points on both sides. And when we place an object in front of the lens, the light will go through the lens instead of reflecting back. For reference, we often point put a center line right through the center of the lens. Now, it's actually easier, I feel, to make ray diagrams for a lens because of that center line than it is for a spherical mirror. When you worked on the ray diagrams for the spherical mirror, you found it was actually kind of difficult to get the rays to converge exactly right. You had to be incredibly careful drawing your angles of reflection and making sure everything was at the right point. A little bit easier to do with these lenses. So let's take a look. Here's a more closer diagram of the convex lens. And I want to put an object in front of this lens and a light ray in front of this lens and see what the laws of refraction says will happen. So I start with a ray parallel to the principal axis. Now, this light ray is parallel to the principal axis, traveling through air, and strikes the glass. Now that means I need a normal line. But remember, this side of the curvature, it represents a sphere where 2f was the center of the sphere. So that means my normal line will go from this point, 2f, which is the center of curvature, to where the light strikes the glass. Now I'm going from air, where light is traveling very quickly, into glass, where light is traveling more slowly. That means I expect the light ray to bend towards this normal line. And it does, but my glass, I'm not going into glass and staying there. When we talked about refraction problems, we generally looked at light traveling from one material into another and didn't spend too much time examining light traveling back out of that material. So this is correct for light, what's happening inside the glass, but at this point, the light's going to exit the glass and go back into the air. So in reality, I need to stop that light ray when it hits the other side of the glass. Like that. Now, I would like to know what happens to this light ray as it exits the glass back into the air. Well, for that, I need another normal line. But this curvature now is based on a circle, the geometry on this side of the lens. And so the 2f over here is now the center of this circle. So my normal line has changed direction. So my normal line is now going this way. Now, because I'm going from glass, where light is slow, into air, where light is fast, I expect my light ray to bend away from this normal line. And it does. In fact, the geometry, looking at the geometry, what ends up happening is a parallel light ray for a convex lens will ultimately be bent through the focal point on the opposite side of the lens. Now this is fairly similar to what happened to a spherical mirror. With a spherical mirror, a concave spherical mirror, a parallel light ray bounced back through the focal point. Now for a lens, a parallel light ray to the principal axis will bend through the focal point on the opposite side of the lens. Also, you can guess what would happen if I sent light from the focal point to this lens. It would get bent so it goes parallel. So a converging lens will bend a parallel ray towards the principal axis and through the focal point on the opposite side of the lens. Well, let's take a look at a concave lens. So again, a ray parallel to the principal axis will refract through the focal point opposite side of the lens. So we're going to do the same example, but now with a concave lens and see how the change in geometry affects the behavior of the lens. So again, I'm looking at a cross-section of lens. So this would be a circular lens, but it would be thinner in the middle. So bulging at the edges, but thinner in the middle. So again, I'm going to start with a ray parallel to the principal axis. And again, I'm going to need a normal line. But now, based on the curvature, the center of this circle will be on the same side as my light ray here. So here is the normal line for where this light ray is hitting the glass. So again, I'm traveling from air into glass. And so my light ray is my speed of light is slowing down. So I expect this ray to bend towards this normal line. So it bends towards this normal line. But again, the glass is thin. So this would be true if the ray stayed in glass the entire time. But again, I need to only consider this ray when it's in the glass. So that's what's happening inside the glass. On the opposite side of the glass, the light ray is going to exit back into the air, which means I need another normal line. So here's the normal line for this curvature. coming from the center of that circle to where the light is hitting the glass about to exit into air. Now, based on the fact that I'm going to go from a slow material to a fast material, this ray should bend away from this normal line as it enters the air. And it does. Now, in fact, this light ray, as long as this lens is symmetric on both sides, this light ray is going to bend in a direction as if it was coming from the focal point on the same side as the incident light ray. So notice that I am now bending this light ray away from the principal axis. So when you're doing your ray diagrams, what you want to remember is a convex lens, thicker in the middle, will always bend the light rays in towards the principal axis. That's why they're called a converging lens. A concave lens will take a parallel ray and bend it away from the principal axis. That's why they're called a diverging lens. So a ray parallel to the principal axis will refract from the focal point on the same side of the lens. So when I'm doing this parallel ray, what comes out on the opposite side of the lens will be in a direction lined up with the focal point on the initial side of the lens. All right, so basically with looking at this behavior, we can adapt our three rules from spherical mirrors and now use them with lenses. So let's tweak those three rules. Well, rule number one for lenses. Any incident ray parallel to the principal axis refracts through the opposite focal point. That's if you're a convex lens, thicker in the middle, or from the same side focal point. That's what we just looked at with the concave lens. So, as the light is going through this lens, if it is a convex lens, it will bend inwards to the principal axis through the focal point on the opposite side. If it's a concave lens, thinner in the middle, it'll bend away from the principal axis as if it's coming from the focal point on the original side of the lens. Rule number two, any incident ray passing through the same side focal point reflects parallel to the principal axis for a convex lens. So if I send light through the focal point on the object side, the real side of the lens, the object side of the lens, that ray will get bent parallel to the principal axis. This is basically the same rule with spherical mirrors, that if the light ray went through or from a focal point, it would then reflect parallel to the principal axis. And rule number three is any light ray passing through the exact middle of a lens will go straight through. Now, this is the equivalent of our rule about the center of a mirror, that any ray that hits goes towards the center of a mirror will reflect back straight along its normal. So these three rules are very similar to what we use with mirrors and a lot easier to understand if I show you them in action. In fact, again, as I mentioned, I think you'll find that ray diagrams for lenses are easier to complete than a ray diagram for a mirror, as long as you draw that center reference line. So, and again, as I mentioned, these three rules are important, so you should write these three rules down on a piece of paper so you can refer to them when you do this week's assignment, which will be a paper assignment and not on the computer. So I'll pause. Good. Write them down. Let's use these rules now to do some ray diagrams. So here I have an object. I have a candle in front of this lens, and you'll see that I've put this center line on the lens for reference. Now, when you're doing a ray diagram for a lens, you don't want to stop when the light hits the glass. You want to always bring your rays to that center line of the lens. So the center line is very important. So again, I'm going to start by drawing a ray parallel to the principal axis, and I'm going to take it right to the center of this lens. That. And you can guess that this ray, based on those three rules, is going to go through the lens and end up passing through the focal point on the opposite side. This is a convex lens, so it's going to bend the light towards the principal axis. So the ray your ray should end and start right at the middle of the lens. So here I end the first ray in the middle of the lens, and then the refracted ray starts at the center line. And this is an example of rule number 1. A parallel incident ray refracts through the opposite focal point for a convex lens. Well, here's where it gets easier than it was for mirrors. Because the next ray I'm about to draw, you can always draw. The simplest ray to draw on this lens is a light ray that goes from the top of the object right through the dead center of the lens. And as we mentioned before, that light ray doesn't bend at all. Goes straight through. This was rule number 3. A ray passing through the middle of a lens passes straight through. And there you have it. I have 2 refractions crossing, so I know where my image is going to be. Here they cross. So again, this light started at the top of the object, so where it crossed must be the top of the image. The bottom of the candle is on the principal axis, which means light from the bottom will pass right through the lens and not get bent at all, which means the bottom of my image must be on the principal axis. So I know that my image here must start from the principal axis and extend to the point where those rays cross. That means I have a real inverted image. Now remember the definition of a real image. A real image is one that I can shine on a piece of paper. If I put a piece of paper where that image is, I would see the image project the image of the candle upside down onto that piece of paper. And you might also remember we mentioned that when you're dealing with a single mirror lens, a real image will always be inverted, and in fact, it works out this way. So we're technically done. If you were doing this question, ray diagram to locate an image, you're good to go here. Just 2 rays will do it. But let's apply the missing rule, which is rule number 2, just to make sure that the light ends up in the correct place. Rule number 2 is I send the light through the focal point on the side of the object. Now again, as this light notice I go to the center of the lens again, and this light ray is going to get bent towards the principal axis. In fact, it's going to get bent so it is parallel to the principal axis. And there you have it. So this is rule number 2. A ray through the same side focal point refracts parallel to the principal axis for a convex lens. All 3 of these rays cross right there. That just confirms the image is in the right place. And there you have it. But you really only need to draw 2 rays to locate the image. And on the next example, you'll see that I recommend always starting with the light ray straight through the middle. So let's move the object where it is away from beyond the focal point to close to the lens to see what happens. Now, again, note that a convex lens is making a real image, and you might remember from spherical mirrors that a convex mirror made a virtual image. So a convex lens makes a real image like a concave mirror. So you can't use the words convex and concave to think about what kind of images are being made. It really just describes the shape. So what you need to remember is a convex lens acts like a concave mirror. So I have the same lens, which means I have the same focal points. What I've done is moved my candle, my object, closer to the lens. And I'm going to use those ray diagram rules to see where the image will be. But unlike before, I'm going to start with the light ray from the top of the object straight through the middle of the lens, because that one does not bend at all. So I suggest you always start with this light ray first. Light from the top of the object right to the dead center of the lens. You need to make sure it's going right through the center, and that will go straight through the lens. Done. Now I'm going to send light parallel to the principal axis to the middle of the lens. And since it's a convex lens, it's going to bend that light towards the principal axis through this focal point. Now, although I'm using the same rules as before, notice that these 2 light rays do not cross on the real side of the lens. And just like we did with mirrors, if my light rays do not cross, I project them backwards to see where they do cross. So I project the first ray backwards, I project the second ray backwards, and I see they cross here behind the original object. And I would get a virtual image. Now, this is different than mirrors. Remember, when we dealt with mirrors, the real image was always on the same side as the object. Well, that's because the way a mirror works, the light bounces off the mirror. But for a lens, the light passes through the lens, so the real side is on the opposite side of the lens. So again, you just can't look at the picture. You have to think about what the light is doing. There is no way for me to stick a piece of paper where this candle is and project an image because the light's not really there. The light is passing through the lens to the other side. It's just when I look this way through the lens, when I look on the side of the object at that lens, what I'm seeing is where the light rays seem to be bending from, and I get this virtual image. Notice that this is a magnified image. In fact, anytime you use a magnifying glass, you're actually using a convex lens, which is why when I use this lens and hold it in front of my eye, you can see this magnified image of my eye. So there you go. So that's how we can, so very simple to do the ray diagrams for a convex lens. So this image is virtual. You cannot project it, but it's on the same side as the object, which is different than for mirrors. Okay. Now let's take a look at a concave lens. Now, a concave lens only creates virtual images. So a concave lens works like a convex mirror. When we had a spherical convex mirror, it also only made virtual images. So a concave mirror could make a virtual image, a real image, or have no image. A convex mirror always produced a virtual image. So an analog for a lens is a concave lens, will always make a virtual image. This ray diagram is a little bit tricky. However, it only does one thing. So once you know how this ray diagram works, you know it for all concave lenses. So again, I'm going to suggest that we send a light ray straight through the middle of the lens because it'll go straight through, and that's the easy one to draw. So simple. Always start with a light ray through the dead center of the lens. Well, I'm going to send now a light ray parallel to the principal axis to the middle of the lens. Except this is now a concave lens or a diverging lens. That means that when the light pops out on the other side, it's going to bend away from the principal axis. So in fact, it's going to bend away from the principal axis as if it was coming from the focal point here on the same side as the object. And this is the rule number 1, and it should say for concave lens, not for convex lens. Sorry about that. I'll fix it under the fine print later. All right, so this is a concave lens. It bends the light ray outwards as if it's coming from this focal point. That's the big difference here. Now, we're actually done. Notice that the light rays do not cross on the real side for the lens. I cannot put a piece of paper here and get an image. But I don't need to do any tricks projecting it backwards because I've already added this dotted line here because the light ray was coming from this direction. I see that the light rays seem to cross right here. So I will get a small virtual image in front of the that would appear to be in front of the concave lens. So a concave lens always makes a smaller virtual image. So there you go. All right, so let's summarize the differences between lenses and mirrors. All right, first off, a convex lens behaves like the concave mirror. That is, both can cause parallel incident rays to converge. Both can make real and virtual images. And just like with the concave mirror, if you put an object on the focal point of a convex lens, you will not be able to find an image on either the real or the virtual side because the rays become parallel. Now, a concave lens, one that's thinner in the middle, behaves like a convex mirror. They only create virtual images that are always smaller than the object. And finally, an important difference to remember is that real images from a lens always appear on the opposite side of the lens from the object. Virtual images appear on the same side of the lens as the object. For mirrors, that was backwards. It was the reverse for mirrors. But that handy tip we said before, that a real image is always inverted from a single mirror or lens, still holds true. So if you're carefully drawing your ray diagrams and you realize that the light from the top of an object is going to create an image where the image is upside down, then you know you're dealing with a real image. And if you stuck a piece of paper at that location, you could project it. All right, so the next video is going to cover a little bit about the lab activity this week. We're using a simulation of lenses for you to answer some questions and to construct some ray diagrams. So I'll also, if I have time, do some more demonstration videos. Next week, we'll look at how to use the lens equations, just like we did with the mirror equations. And then we'll be pretty much wrapping up optics at that point. Okay, see you later.